Breaking through 1.5 meters of ice demands a megastructure of incredible power. The icebreaker. These behemoths keep the world's shipping lanes open during the harshest of conditions, making them vital to the global economy. Now comes the construction of a vessel that can break ice and carry cargo at the same time. The Arctic Icebreaking Container Ship. It will measure 169 meters, weigh nearly 20,000 tons, take 11 months to build, and revolutionize Arctic shipping. Over the next 11 months, a team of 300 engineers and workers from the shipbuilding firm Acker Yards will combine their efforts here in northern Germany to construct the Acker CS 650. A world's first, an ice-breaking Arctic container ship. Project manager Hans-Jörg Wenzel will orchestrate delivering this $120 million marvel to the Russian mining company Norilsk Nickel.
My job is to follow up the project from the very first beginning, from the awarding of the contract until the end of the guarantee period of the ships.
That's right, a guarantee. Norilsk Nickel's contract contains a caveat. They can return the ship for a full refund if it fails to perform as expected. For their money, Norilsk Nickel will be getting a ship like no other. Icebreakers rely on 3 key components: a strengthened hull, a wedge shape, and the power to push through solid ice. Ordinary ships can't risk even brushing past ice. But icebreakers can carve a channel 50 meters wide. They do it with power and strength. Most icebreakers have shielded propellers at both the bow and the stern. They use their momentum to push their front, called the bow, up on the ice. The bow is specifically designed to break ice. It consists of an inclined wedge that forms an angle of about 20 degrees with the ice surface. As the icebreaker advances, the bow rides up on the edge of the ice until the ship's weight becomes so great, the ice cracks. As it breaks, it's forced downwards along the sides of the bow. The Acker CS 650 also features a revolutionary structure, a newly developed propulsion system, and a double-acting hull. These innovations allow it to carry cargo and break ice. Most ships sail bow first, not the Acker CS 650. In icebreaking mode, it sails stern first or backwards. Sailing backward gives the ship the power to break through ice 1.5 meters thick. In light ice conditions or open water, the vessel turns 180 degrees and sails traditionally bow first, making it double acting. The Aker CS650 can navigate icebound Arctic Ocean routes unassisted year-round. Not having to hire a separate icebreaker will save its owners millions of dollars a year. Breaking ice taxes the structural integrity of the toughest ship. So icebreakers must be extra strong. Since the 1960s, mining in the Arctic has spurred the construction of icebreakers that can transit as far as the North Pole. They not only keep vital shipping lanes open, they provide the platforms to conduct polar research year-round. Even the earliest polar explorers used ice-strengthened ships. They wrapped iron bands around the hull and nailed metal sheeting to the bow, stern, and keel. But over time, scientists discovered something that makes ice especially dangerous. Oceans contain different types of ice. Sea ice forms from frozen ocean water. Icebergs actually originate on land, from freshwater ice shelves or glaciers that carve into the ocean. Icebreakers must sail safely in all ice conditions. Before constructing a $120 million vessel, the Aker Arctic Research Company specializes in Arctic technology development and tests icebreaker models in different ice conditions. Mikko Niini is the head of their state-of-the-art research lab in Helsinki, Finland.
We are a combination of ice model testing facility and a naval architectural company. So this is in fact a unique combination which doesn't exist in the world.
They've been designing icebreakers for over 50 years.
What we already had learned here in the Baltic Sea and partly also in the Caspian projects was that with some new propulsion devices it was possible to create independently operating cargo ships, also for very heavy ice conditions.
2.5 years ago, Aker Arctic tested their revolutionary one-ship-does-all design.
We showed Nordic people how much cost saving the implementation of this new technology could bring to them. So they got very interested.
They could save millions of dollars per year. For that kind of money, every single part of its function must be tested before and after construction.
Typically in ship design, you do several, we call iterations. You have first done one design, and then you check everything, and if there is something which you think that need improvements. So any improvement always has some other consequences.
Aker Arctic's labs have gathered a wealth of knowledge from designing and constructing icebreakers. They've tested more than 300 design models and even developed their own model ice. Natural ice crystals vary in shape and structure, depending on the conditions they form under. Geophysicist Mika Makela makes the ice that Aker uses to test their icebreaker designs. Aker Arctic has designed equipment and machinery solely to create very small, even ice crystals.
If we take a freshwater ice, it's really large crystals normally. If we take just a normal seawater, it has a smaller crystals because there is salty water inside, so actually the crystal size will be even smaller. And here we have an even smaller crystal size, and that's also one of the reasons why it's so weak.
This originally patented model ice is the most reliable material to model different ice conditions.
Normally we always make a level ice or ice sheet here, and after that we can make different kind of ice conditions. We can make a channel, we can make an ice ridge. Of course the ice is also different if we think about where we go. We try to make the ice so that it's enough close to the place where actually the boat is going to.
This test basin measures 75 meters by 8 meters and 2 meters deep. It takes 4 hours to spray ice onto the saline water and allow it to freeze into a smooth ice sheet.
We actually spray the water and it's frozen actually on the water sheet. So normally ice just builds up from the bottom when it freezes, but actually we build it so that it builds upwards.
Meanwhile, in an outer chamber, the research team prepares the model for testing.
Today we defined ice thickness, and we want to know with a certain power level is the vessel able to reach critical speed.
First, the ice must reach the perfect hardness, thickness, and texture. The team takes several samples to ensure perfect ice. In the first test, the model ship plows full speed into the virgin level ice sheet. They film this test from above, side on, and below. In this test, they break up the ice and let it refreeze to approximate a natural ice field. Once testing is complete, they analyze the data. The team then tweaks the design to optimize its ability to break ice. Then the naval architects send the designs to Germany so the draftsmen can turn them into blueprints. Project engineer Matthias Linnemann began working on the Aker CS650 2 years ago, after it was model tested in Finland.
We get from our Finnish colleagues the basic design, which we corrected the design for our building facilities.
The drawings prepared by the designers describe the whole ship from the inside out.
So we start with a double button. It's the area where the ballast tanks for the ship and also the pipe tunnel. This is the first part which lay down in the dock.
From the structural drawings, they calculate the size and shape of the steel plates.
When we get the design, we have to modify it for our production, and this plan shows the blocks of the ship.
The team translates the plan into cutting sketches for ordering the steel. Then they'll assemble the ship in sections. The first section they lay down is the double bottom. The hull is then attached. Icebreakers can't have weak spots. Every single element must be strengthened and tested. The sea is no place to discover a mistake. September 2007. Ruki Steel delivers the plates from Finland to Akka's twin German shipyard. The 15 rear components will be constructed in Wismar, on the Baltic Sea. The 12 components making up the ship's front half will be assembled in Warnemünde, in northeast Germany. Project manager Dr. Wenzel prays nothing holds up construction, and the technology performs as the models and simulation predict.
We have a huge time pressure to manage all the contracts we have to deliver in this year. The whole team of the yard is very busy. It's not a copy of a standard container ship, so they need more time to understand how the technique of this ship works.
This icebreaker will weigh nearly 20,000 tons, involve 300 workers, consume 4.5 million man-hours, and cost $120 million. It'll contain enough steel to build the Eiffel Tower. Enough paint to coat 12 Golden Gate bridges. And 215 kilometers of cable. The Akka CS650 will carry containers filled with raw metal ore across icebound seas from the Yenisei River to Murmansk in Russia's far north, high in the Arctic Circle. With delivery looming in 10 months, construction must begin on time. The timetable allows no room for mistakes. Shipyards build icebreakers the same way they build other ships, by assembling their component parts into sections, then welding the sections together. Here in the Warnemünde shipyard, where they're building the front half of the Akka CS650, workers prepare the steel profiles and plates for construction. They transfer the plates to the cutting shop to be cut to size in large basins. Water reduces the toxic emissions produced by the cutting laser. These lasers are computer programmed, but an experienced engineer supervises each procedure. Any mistake would derail the ship's delivery. Some steel plates will come directly here to the milling machine to have their outer edges perfectly straightened in preparation for welding together. Workers join up to 7 sheets to make one huge steel section. But other steel plates and profiles must first be bent. Workers program the desired shape into a robotic bending machine, which shapes the metal using 1,000 tons of pressure. Gantry cranes and multi-wheelers move the prepped steel plates and profiles to the dockyard assembly lines. Each vehicle can carry 400 tons. Gantry cranes handle the heaviest loads. Each stands 33 stories high and can lift 600 tons. They open the warehouse roof so the crane can transfer the ship sections into the dry dock. The shipyard prefers women to operate the cranes. The theory? They keep their cool better under stress. Vital in such a dangerous operation. Imagine the damage from 600 tons of high-flying steel. After constructing the ship's sections, workers attach the pipes and cables to the hull. A system of rigs and trolleys gives them complete access everywhere. The job takes more than 100 welders, but each knows exactly which section to weld. No time for mistakes or miscommunication. They need to fit this giant jigsaw puzzle together on the first try. Norilsk Nickel wants to take ownership of their icebreaker ASAP. With so much at stake, construction continues around the clock. It's December, and construction has been steaming ahead for 3 months. Akka's shipbuilders put the plates and profiles into larger sections and hauled them here to the paint shop. The shop strictly controls humidity and temperature to guarantee the best finish. First, they blast the steel with high pressure to remove the shock primer. Then they paint the ship in sections. That requires enough paint to fill more than 600 bathtubs. After painting, they transport the sections to the dry dock shop for the next phase of assembly. Here, they're moving the ship's deck house. But no one's driving this multi-wheeler. You're looking at the ultimate remote-controlled vehicle. Each part weighs nearly 400 tons and takes the multi-wheelers 3 hours to move. One month later, workers complete the Akka CS650's component parts. Now, to fit them together. This dry dock warehouse towers many stories high and stretches the length of 3 football fields. The door is so huge, it takes 45 minutes to open. The completion of the double bottom of the ship's front half marks a milestone in the icebreaker's construction, so workers celebrate with a dry dock ceremony. The first component they deposit in the dry dock is the double bottom. They lay coins beneath the keel for good luck. They'll retrieve the coins when they float the ship and present them to the client on delivery. But it'll take more than luck to deliver this groundbreaking icebreaker on schedule and in perfect order. The ship contains nearly 8,000 tons of steel, making it strong enough to go anywhere. Welding takes over 5,000 man-hours, a skilled and dangerous job. After completing the shells of the 2 halves, they begin the outfitting. One of the most crucial jobs is installing the engines. Cranes place three 56-ton diesel engines into the back half. Each engine can produce 6,000 kilowatts. Together, in 1 hour, they could power 20 American homes for a month. This enormous power supplies the ship's main propulsion component. A big electrical motor called an azipod unit. This azipod has a 4-bladed propeller more than 5.5 meters in diameter. It's not only big, it's versatile. It can double as a rudder. It rotates 360 degrees around the vertical axis, giving the icebreaker full maneuverability. In heavy ice, the vessel moves stern first to break its way through. In light ice or open water, the vessel turns 180 degrees and sails traditionally, bow first. A regular container ship is nowhere near as maneuverable. It takes twice as far as the Aker CS650 to stop and turn around. The diesel azipod packs enough power to break through 1.5 meters of ice. While operating, the Aker CS650 can burn 25,000 liters of diesel per hour, so it must refuel before every voyage. It's an inconvenient and expensive drawback, but it is avoidable. Nuclear-powered icebreakers, like the Yamal, rarely need to refuel. They can remain at sea for up to a year. Russia has a fleet of 8 nuclear icebreakers. Most of her minerals are buried near icebound Arctic shores. So icebreakers are essential for Russia. The Yamal is fueled by 2 nuclear reactors, each providing 171 megawatts of power. That's enough combined energy to power around 400 American homes for a month. Built in St. Petersburg in 1992, the Yamal has a big job: to keep shipping lanes open. She's one of the few surface vessels to ever reach here. The North Pole. The only difference between a nuclear icebreaker and a diesel one is its power source. Three propellers drive the vessel, each with 4 7-ton blades. The 160-ton nuclear reactors that provide the steam for propulsion are encased in steel, high-density concrete, and water. The nuclear reaction furnishes endless power, but yields radioactive waste. The main drawback: storing and disposing of that waste. It takes hundreds of thousands of years to decay to a safe level of radioactivity. These ships must cruise in cold water to cool their reactors, so they can never visit the southern hemisphere, since they'd have to pass through the warm tropics. Russia's icebreakers don't just transport minerals. To bring in foreign currency, the Yamal is chartered for other operations, particularly tourism. One of its most popular trips is a champagne reception at the North Pole. How many people can say they've been swimming in the polar ice cap? The Yamal's most important role is providing a platform for exploring resources at the North Pole. And transporting these resources will become the Aker CS650's urgent job. Norilsk Nickel eagerly awaits delivery of the Aker CS650, an icebreaking container ship that promises to revolutionize their company and save them millions of dollars. Time is money. And these Russian clients don't want to wait a minute over their delivery date. "7 months into production, and the two halves of the ship are complete. The back half of the ship sits in the Wismar dry dock. The front, 72 kilometers away in Warnemünde. Now to join the two halves. They tug the front half around the coast to Wismar. The trip should take about 10 hours. In bad winds, several days. Once they bring the two halves to the site, they'll join them together. To begin, they flood the dry dock. But they hit a snag, a traffic jam in the dry dock. A container ship next to the Aker CS650's back half bars the way. They park the ship's front half nearby in the outfitting quay while they unsnarl the jam. The container ship must be moved out before the icebreaker's front half can come in. Once the dry dock fills with water, tugs remove the dock gate and two more tugboats enter. They gingerly guide the parked ship out to ensure it doesn't collide with the side of the dry dock or the back of the icebreaker. Then they float in the front half of the Aker CS650, aided by tugs at the front and back. Next, they pump 2.5 meters of water out of the dry dock to float the two halves together. It takes 3 more hours to carry out the precise measurements to connect the two halves.
This team is checking the real position of the foreship related to the aft part. And that has to be very accurate. We are speaking about centimeters they have to consider. And he has to control very accurate pumping the water out of the dock where it is positioned. This is a 3D measuring system. It's a laser-based measuring system, very precise. You can measure exactly by 1 millimeter. If it is floating, it can move in all directions. And that makes a little bit complicated. So they have to lower the forepart, very controlled, keep it under control all the time.
The front half is still floating, while the back half is weighted down with ballast water. They'll pump out the water to bring in the front half slowly, until the seam becomes parallel. Any mismatch would spell disaster. When the two halves are aligned, they can weld the ship together. Once complete, they have a whole icebreaker, ready for final outfitting and testing. Now they'll find out if this icebreaker can face Arctic ice. $120 million hangs in the balance, as Dr. Wenzel hopes the Aker CS650 passes an exhaustive battery of tests. Tests designed to push every element of this revolutionary ship to the limits of its endurance.
You know, everybody is nervous when we start a sea trial, but that is part of the job.
Any malfunctions could set back the delivery by months, costing Aker millions of dollars, and client Norilsk Nickel both time and money. They subject the icebreaker to an intensive series of tests. At the dock, it's time to switch on the electrical systems, cooling pumps, and basic engines. It's easier to make corrections here than at sea. But before delivery, they send the icebreaker on her first sea voyage. Her sea trials will last for 4 days. Reinhold Krolov has the unenviable job of shepherding the Aker CS650 through final testing.
We have, before sea trial, made a time schedule, and in this it is written in which hour we have to make which test. For the whole test, we have to test the navigation systems. We have to make the speed trial. The speed is over the contract speed. We have made turning circle, and the turning circle for this ship is under 300 meters, and that is very, very small.
To put that in perspective, the turning circle for a regular container ship the size of the Aker CS650 exceeds 500 meters. The new icebreaker passes all its trials. They carry out the final test, the bollard pull test, at a special facility here in Norway. This test consists of securing the icebreaker to the dock with bollard shackles and running the main propulsion machinery at its highest level for 6 hours. The 10-centimeter wide, 2.5-kilometer long cables can withstand 600 tons of stress. Imagine tying your car to a gate and putting your foot on the gas for 6 hours. Now magnify that by 100 times. No ship undergoes a more physically demanding test.
This was an endurance test. 6 hours, full speed with the propeller, but the ship is fixed.
Even steady at 130, you almost had 140.
Steady 130, ja. MK-Brücke, das wird angekommen.
It's an extremely high challenge for the ship itself. Everything is rattling and shaking.
150.
Everyone hopes the ACA CS650's structural integrity will hold. If anything electrical or mechanical was going to fry or melt, it would have done so by now. The ship survives. Now, to celebrate. It's the end of July, and after 2 years and 500,000 man-hours of design and construction, the ship is ready for delivery to the client. They celebrate with a lavish naming ceremony.
Вітаю тебя, Мончегорск. I name you Мончегорск.
Dr. Wenzel bids a proud farewell.
It's a good feeling to finish such a sophisticated kind of ship we did the first time, and yeah, it's a good feeling.
The ACA CS650 becomes the property of Norilsk Nickel. She's now ready to take on the ice-clogged seas of the Arctic.